We're going to take a whistle-stop tour through quadratics. This is a big topic and there are a lot of quite sophisticated bits of maths within it, but a lot of it is content that you will hopefully have encountered at GCSE, especially at the higher level. So although you shouldn't be too concerned if there are pieces within this that don't quite make sense, you should definitely make an effort to work on those areas because you will be relying on them and using them for quite a lot of the course that we're going to be doing. So just to give you some sense of where we're heading with this, we're going to assume that you've seen quadratics before. So we will whiz through things like factorizing, completing the square. But I will try to give you a little bit more background or perhaps a different insight. We'll think about the why a little bit more than perhaps you did when you first learned about this topic. So we're going to go into exactly what a quadratic is. Our definitions, as you're going to discover, are really important in maths. We can't really say very much at all about anything unless we can agree on what the thing is we're describing. So our definitions are crucial. How we work with them, what are the common tools that we bring to the table when we're dealing with quadratics, and finally why they're so important. What is it about these functions that makes them such a key part of a higher algebra course at GCSE and a fundamental starting point for the algebra that you'll do at A-level and beyond. To start with, what I'd like you to do is try to write down everything that you can about this expression, 2x squared minus 5x minus 3. And try to treat this as a chance to demonstrate what you can do when it comes to quadratics. I'd recommend you take a little bit of time with this and you spend some careful thought, and then perhaps after you've watched the video and done some other questions, you come back to it again and you see if there's anything you can add or anything you could correct or update about the write-up that you've made. As I said, we're going to begin with some definitions. So let's start with this one. A quadratic expression is like that expression I've written on the left, 2x squared minus 5x minus 3. You'll notice the thing that's lacking there that you might be used to seeing is an equals. Generally speaking, when you're dealing with quadratics, you might think quadratics and quadratic equations are essentially synonymous, and sometimes we use them in that way. But a quadratic expression is specifically a bit of algebra that potentially involves an x squared and an x term and a constant. Now, there's a little condition in there. We're being very precise here, pedantic almost, but that's maths for you. Ax squared plus bx plus c, where a is not equal to 0. In other words, if you don't have an x squared term, we wouldn't really call it a quadratic. That will be a linear expression, something x plus something. Having an x squared term in there as well makes it into a fundamentally different kind of creature. As you can see from the parabolic arc being demonstrated by the ball that's being fired through the air, this is a curve rather than a straight line, and the behavior of quadratics is fundamentally more complicated than straight lines. Now, a quadratic equation you might be more familiar with. When you see that, you immediately think there's something I need to do with this. Unlike an expression where there are other ways to write it, you could factorize it or you could write it in a completed square form, but with an equation, you have an implicit purpose behind it. Your aim is going to be to solve the equation. You're interested in finding out what values of x make that algebraic statement true. And there are various ways of doing that, and often they involve the techniques that we've mentioned. You could factorize, for instance, and use that to help you work out what values of x make your quadratic expression on the left equal to 0. And the last thing is a quadratic function. And if we're talking about the graph of a quadratic, we're representing that function in a graphical way so that we can see it as a picture in front of us. In that case, we might have y equals ax squared plus bx plus c, or f of x equals ax squared plus bx plus c. We can think of this quadratic now as something which takes an input value and manipulates it somehow and churns out an output value. And we can ask questions like, what's the largest possible value we can get? If you look at the animation on the screen, there is a maximum point that the ball in motion gets to, and we could calculate when that happens and exactly how high it is at that moment. Other common questions would be, when does this function give me a 0? It's called a root of the quadratic, a value you can put in that produces 0. So you can see there's lots of close connections between the functions, the equations, the expressions. but having the right terminology is helpful for making sense of it and tying it all together. And bear in mind, if we're dealing with a function, it doesn't have to be on a graph, but very often to help us represent inputs and output values, we think of x and y. So we have input values of x that go into a function, and then the outputs will be mapped onto a graph so that we can see a picture of all the possible inputs within a given range and all the outputs that correspond to those inputs. It's worth pointing out at this point that your calculator, the Casio Class Wiz, has a quadratics mode. So all of the work that you'll be doing, although it's important to understand and be able to factorize and to complete the square and use the formula, a lot of what you would have used that for at GCSE is now done for you, more or less, by the calculator. For that reason, there will rarely be more than a single mark for just solving a quadratic equation. It's assumed that you will use your calculator to do that in most cases. What you will need the other techniques for is for dealing with situations where there's extra algebra thrown in. Instead of 2x squared minus 5x minus 3, it might be kx squared minus 5x minus 3. Or they might be asking you to find out when that quadratic crosses a straight line. And so there will be some solving of quadratics involved in the question, but it won't be as straightforward as look at the three numbers, put it in the calculator, no need to do any thinking. If you want to investigate that, press the menu button on your calculator and then search for option A, where you can just press the button with an A on it, which I believe has a little minus sign in brackets. It's on the second row up in the black buttons. You can jump straight to the quadratic section from that. It gives you two options then. Simultaneous equations is option 1 and polynomial is option 2. A quadratic is the first sort of polynomial that you're going to deal with that is more complicated than just a straight line. The next polynomial up would be a cubic polynomial, which means you might have an x cubed term as well as the x squared term or an x term and a number. And then the calculator will let you deal with cubics and quartics as well as quadratics. Once you choose degree 2, meaning the highest power of x that appears is the power of 2, x squared, then it will allow you to put in values for a, b, and c, and it will tell you straight away what the solutions are to the equation formed by your expression equals 0. It will also give you information about the maximum or the minimum point that your curve reaches. And if you want some additional resources for looking at quadratics, try typing a quadratic expression or equation into geogebra.org or into wolframalpha.com, and it will tell you a lot more and show you some graphs. To talk a little bit more about the terminology, here's a few quick examples of quadratic expressions. They can look like all sorts of things. 1 minus x squared is not necessarily written in the same way round as ax squared plus bx plus c, and it doesn't have an x term, but that doesn't stop it being a quadratic expression. 3x squared minus a half x plus 2, it's got a fraction in there, but again, that's not a problem. The next one, x had 4 times x minus 1, is what we call factorized form, and that can be very helpful depending on what we want to find out about our expression. And then the last one, 2x minus 3 in a bracket squared plus 5, is completed square form, which again is useful for different reasons. A quadratic equation may be very similar to a quadratic expression, but you'll notice for each example here there is an equal sign. So an equation is something which, by its very nature, has potentially solutions. Now, unlike linear equations that always have one solution, as long as they're not just a straightforward contradiction like x had 1 equals x had 2, which has no solutions, well, quadratics may have two solutions, and they may also have just one, and it's also possible that they have no real solutions. In other words, there are no real numbers, no numbers in the number system that we usually use that will solve that quadratic. So for example, x squared minus 4 equals 0. We can find a couple of different numbers that work there. 2 squared is 4, so 2 squared minus 4 is 0, and negative 2 squared minus 4 is also 0. But if we had x squared plus 4 equals 0, you would struggle because there are no numbers that you can square and get a negative answer until you create a new number system. The quadratic graph, generally speaking, having it in a factorized form or in a completed square form is a helpful way of converting the algebraic form of a quadratic into a graphical form. What's useful about it is that you can see not just where the curve crosses the x-axis, which is equivalent to solving the equation, and not just where it has its lowest or highest point, but you get a sense of the entire function, the kind of numbers that come out from it for all the different values of x that you're interested in. Now, we talked about the various formats. The standard format that I will often refer to is the format that your calculator will expect if you're putting numbers into it. So often we rewrite quadratic expressions so that they all fit this kind of standard format. 2x squared add 4x minus 16, for instance. That allows us to see quickly and easily whether they're equivalent to each other or rough things about it. For instance, this is a positive quadratic, so if you drew the graph, you would expect it to look different to what I would call a negative quadratic. If the number in front of x squared is negative, we'll get a different shaped graph to if the number in front is positive. And we'll look into that more in a moment. The factorized form is a form where the entire quadratic expression has been written as two simpler expressions multiplied together. There'll be two linear expressions. So in this case, our expressions are 2x minus 4 and x plus 4. And that form is helpful for solving an equation, particularly if you've got an equals 0. And the final form here is the completed square form, which looks like more work, and it's often something that students struggle with a little when they first come across it, partly just because they're not convinced of the utility of it. But hopefully we're going to demonstrate both in this video and later on how valuable it can be to have a quadratic written in the completed square form. Just a little hint before we move on here. If you were trying to solve an equation and the thing you wanted to make the subject appeared in two different places, you're going to have some difficulty in rearranging. If you have a completed square form, the variable you're interested in only appears in one place. Somehow the two brackets have been made into the same bracket twice, which allows you to write it as something squared. And that means that you can always rearrange to make x the subject. There are other advantages to completing the square as well, which we'll talk about later. And finally, applications. Why do we care about quadratics? Well, in essence, they are the first interesting type of graph in some sense. They're the first sort of graph, the most basic of the curves that you will deal with. So straight lines are important and useful, and nobody would doubt that or question that. But quadratics allow us to start modeling things that are non-linear. And there's a lot of things in the world that are non-linear. Projectiles are the first classic example, like the animation you saw at the beginning. If somebody jumps off a ski jump, or if you fire an arrow, or if you throw a computer out of a window, it's going to follow a path through the air which looks like a quadratic graph. And that is all to do with the fact that gravity is pulling down on it in the same direction constantly, and there are no other appreciable forces acting on the object. If there are other forces, if the thing has been designed carefully so that it's in the shape of a paper aeroplane, then other forces such as lift and drag and so on will have more of a significant effect. But if you can minimize those forces, then you will find the path of your object follows very closely the path of a quadratic. And being able to deal with the quadratic equations allows you to calculate the range of your crossbow, or the distance you're going to travel when you come off a jump, or how fast you need to be riding your motorbike in order to make it over the top of the truck that you've set up behind your ramp, whatever it might be. Economics is one which is still very real, but somehow more abstract than things being thrown out of windows. But very often we get a situation in economics, even if we model things very simply, where curves like quadratics pop up. Think about a situation where you're selling ice creams and you've got two different pricing models in mind. You could sell ice creams for £4 each, and you would sell some of them because people will buy £4 ice creams if they particularly want an ice cream, especially if they think it's a really good ice cream. But you wouldn't sell as many probably as if you dropped your price to 50p. Then you would sell loads of ice creams. In fact, some people would even buy 2 or 3 because it's so cheap. Now, neither of those is necessarily a bad business model. It depends how you want to sell your ice creams. You could sell lots of them and make a very small amount of profit on each one, or you could sell just a few and make a lot of profit on each one. And there's a trade-off between those two, and there will be a sweet spot somewhere in the middle. And finding the sweet spot is equivalent to finding the maximum point on a quadratic curve. Maybe charging £2.25 per ice cream is the sweet spot. It's not so cheap that you're hardly making any money, but it's not so expensive that you're driving customers away. And the final one I've got here is rocket science. Anything you're going to do with the motion of objects is going to make use of quadratics in some sense, or potentially more complicated algebraic objects. But the force of gravity itself is indelibly connected to quadratics, because if you go 4 times further away from an object, the force of gravity that you experience is 16 times lower. There's an inverse square law at play in there. And the fact that there's something squared means that the calculations that we require when we're dealing with, say, travel in outer space or moving objects into orbits, it all comes down to an understanding of how quadratics work, and then the more complicated objects that quadratics lead us on to. So, solving by factorizing. Let's start with a little bit of a thought experiment. I'm thinking of a number right now. I've written it down. You can't see it, but I can. Now I encourage you to think of a number, come up with your own number. Feel free to change it after you find out more about what I'm going to do with the numbers if you like. I don't mind. Whatever number you pick, here's my claim. I will be able to predict with absolute certainty the product of our two numbers. So once we've both written our numbers down, we reveal the numbers, we multiply them together, and whatever that answer is, I knew it in advance. That's my claim. I want you to pause for a minute and ask yourself how I could possibly do that. What's the trick that I'm making use of? And kind of part of the same question, what must my number be, given that I know for sure what our two numbers will multiply together to make? Pause and have a think, and when you think you've got it, you can continue. Okay, let's investigate a few different cases here, because it seems like an implausible claim. To be able to say anything at all about the product of two numbers when you only know one of them is a bit of a stretch. I could say, well, if I write down a number like 4, then when we multiply our two numbers, the answer will definitely be even, right? Well, not necessarily. You might write down 1/8, and then our answer is a half, so that doesn't work. If I write down a number like √2, I could say, well, maybe the answer is definitely irrational. But you could write down 3 over √2, and then when we multiply them, we get the answer of 3. In fact, I can't really say anything at all about the product, except in one very special case. And to demonstrate that, let's look at a few examples. Imagine our two numbers are a and b, and they are both positive. When we multiply them together, we get a positive answer. Well, what if my number was positive, but your number was negative? Then we'd get a negative answer. Okay, vice versa. My number is negative, your number is positive, the result is negative. And finally, they're both negative. Well, now when we multiply them together, we get a positive answer. What's missing from the right-hand side? Because that looks like a complete enumeration of all the different cases. Well, it turns out there is a number which is neither positive nor negative, and that is 0. And because any combination of either positive or negative numbers, when you multiply them, gives you either a positive or a negative number, the only way we can get 0 as a product is if 0 is also a factor. So maybe my number is 0, in which case I know for sure the product will be 0. 0 multiplied by a positive number is 0. 0 multiplied by a negative number is 0. And even if my number wasn't 0, you could make the product 0 by making sure your number was 0. Whether or not my number was positive or negative would have no effect. And there's one final case, I suppose. We could both choose 0, and yet the product would still be 0. So it's true to say that if a times b is 0, then a is 0 or b is 0. And when we make that claim, the word or, mathematically, is the inclusive or. It's not the same as saying you can have chicken or garlic bread with your pizza. That would be an exclusive or, because if you choose chicken, then you're no longer allowed garlic bread. And if you choose the garlic bread, you can no longer have the chicken. This or is essentially a is 0 or b is 0 or possibly both. It's like you get a prize if you mow the lawn or trim the hedge. Well, if you mow the lawn and trim the hedge, you still get the prize because you've satisfied at least one of the conditions. So that covers all the possible cases. And this zero product principle, as I call it, is the essence behind the entire concept of factorizing quadratics. If we have x minus 2 multiplied by x plus 3, then either that first factor, x minus 2, must be 0, or the second factor, x plus 3, would have to be 0. And therefore either x is 2 or x is minus 3. Those are the only two possible numbers that will satisfy the equation. In other words, make the equation a true statement. Here's a quick example then. If we're looking at this, it's often tempting to try to factorize the left-hand side. That won't tell you anything useful. If you've got two numbers that multiply to make 1, there's nothing helpful in that. But if you've got two numbers that multiply to make 0, then we can start using our zero product principle. So the first thing I do is rearrange so we have our quadratic in the standard format with a 0 on one side. Then we can factorize, we can use the zero product principle, and then we've got an entire complete list of all our solutions. You can and should get into the habit of testing these. Try 4 squared minus 5 4s add 5 and see if you get 1. Try 1 squared minus 5 1s add 5 and see if you get 1. Go right back to the original question as far as possible and test your results back in that equation, see if they really work. Now you should be able to have a go at some of the questions from your Pure Year 1 book, exercise 2A. Next trick we have up our sleeves when it comes to quadratics is completing the square. It's a strange kind of expression, and there are ways of interpreting it with reference to actual geometric squares, but we're going to think of it more in terms of a number squared because it's a lot easier to see how that connects algebraically. Before we begin, it will be helpful if you work through these 6 questions. They shouldn't be massively complicated, but if you work through each one and ask yourself, what do you notice, what do you wonder about the results, that will help you hopefully to make sense of the underlying logic behind this technique. So pause the video, try these 6 questions, and when you're done, unpause. We should have, for the first one, x squared add 10x add 25, the next one, x squared minus 14x add 49, and so on. For the final 3, every single expression can be factorized into 2 brackets which are the same as each other. So x add 3 times x add 3 might be the format you've used, but because the 2 brackets are the same, we can write it slightly more simply by writing x add 3 all in a bracket squared. And that's what's important about those. D, E and F represent algebraic expressions which are perfect squares. And in particular for the ones with whole numbers, you can try this out. If you pick any number, any whole number you like, square it, add 6 lots of it, and add 9, you will always end up with a square number for your answer. And that's because x squared add 6x add 9 is exactly equivalent to x add 3 in a bracket squared. It'll be the square of the number that is 3 higher than the number you chose to put in the first place. Now, most quadratics are not perfect squares, but all quadratics can be thought of as a perfect square plus or minus a bit. Think about, for instance, x squared add 6x add 10. That would just be the same as x add 3 in a bracket squared add 1, because x add 3 in a bracket squared gives you the x squared add 6 squared add 9, and the extra 1 turns that 9 into a 10. So in general, and this does look a little algebraic, so read it carefully and you'll be able to make sense of it. If you square a bracket with an x and a number, then what comes out the other side when you expand it is 2 times the number in the bracket for the coefficient of x, and then the square of the number in the bracket for the constant at the end. And if you check back with questions A, B and C, you'll see this being played out. 5 squared is 25, so there's a plus 25 at the end for question A. Negative 7 squared is positive 49, so there's a 49 added on at the end for question B. In fact, in every case, you'll find it's plus something at the very end, because regardless of the sign of the number in the bracket, we're always adding the square of that number at the very end. So whether it's plus 5 or negative 7, at the end we're squaring that number, be it positive or negative, that gives us a positive result, and then we add it on. Even when there's fractions involved, as there are in C and F, you can still see this pattern being played out. If you have x add 3 over 2, and you multiply it by another bracket x add 3 over 2, then you'll get 1.5x's plus another 1.5x's, which gives you 3x's altogether. So even when we have odd numbers in front of x, we can still apply this idea. The trick is to start with a quadratic written in the standard form and then recognize that halving the number in front of x is the quickest, simplest way of working out what value goes inside the bracket. And once you know what value goes inside the bracket, you know what the extra bit added on would be if it were a perfect square. Let's go through an example, and hopefully this will trigger your memory about this topic or help you to understand what's going on and why. In this example, we're asked to complete the square and hence solve the following equation. Completing the square is by no means the only way to solve this equation, but that's the method we're going to use this time. And remember, completing the square is not only for solving equations, it's also for other things that we'll get onto later. But the first thing we need to do if we want to write this expression in completed square form is look at the x coefficient, that's the number in front of x, and halve it. And that will tell you what number needs to go inside the bracket. So the first thing I'd write down is x minus 7/2 in a bracket squared. More things will follow in a moment, that's why I've put dots after this. But that's the very first term I write down. The other small thing I want to mention here is that whenever we have a non-whole number in maths, generally speaking, from A level upwards, you will find that our natural preference is for a top-heavy fraction as opposed to a mixed number or even a decimal a lot of the time. There's nothing wrong with writing 3.5 in there if you want instead of 7/2, but not everybody is going to be able to say, oh, 3.5 squared, that'll be 12.25. But most of you will be able to quickly and easily square 7/2 by squaring the top, 49, and squaring the bottom, 4. So there are definitely advantages to having a top-heavy form for the fraction. If we were writing it as 3.5, we're going to have all sorts of issues with ambiguity with that notation, because in algebra, when we write two things next to each other, we assume it means they're multiplied together. Writing a 3 right next to a half will make it look like we're doing 3 multiplied by a half if we're not careful. So in general, we steer clear of that entirely. Stick with top-heavy fractions and you won't go far wrong. Now the next step is to say to ourselves, essentially, this is the type of squared bracket that will generate for us an x squared and a minus 7x. And that's all well and good, but of course that's not the only thing it will generate. It will also generate whatever the square of that number in the bracket is. So we subtract the square of that number. That way, we leave ourselves with something which is exactly the same as those first two terms. These things are identical. So we've essentially completed the square by ignoring the constant and figuring out exactly which squared bracket would produce the first two terms that we need. And then because there will also be an additional term generated, we subtract it, get rid of it, and we're left with just the first two terms. All that we need to do next is add the remaining term. We put the plus 5 back in at the very end, so that now what we're looking at is identical to the entirety of the left-hand side from the very beginning. And then you just need to simplify. A good idea here is to write the 5 as a fraction of 4. Call it 20/4, and then it becomes a bit easier. We're taking away 49 quarters, but we're adding 20 quarters. So overall, we're taking away 29 quarters. And this is the completed square form. This is fully simplified completed square form. And there are plenty of things you can do with that. But what we've been asked to do in this question is to solve the equation. The great thing about this is that x only appears in one place. That wasn't true of the original form. We had an x that was squared and another x that was multiplied by -7. So you can't easily make x the subject of that equation. But now it's in completed square form, we can make x the subject. All we need to think of is the series of steps that have taken place to convert x into x minus 7/2 all squared, take away 29/4. So if we add 29/4 to both sides of the equation, and then we square root both sides of the equation, and then we add 7/2 to both sides of the equation, we will end up with x on the left and a number on the right. More precisely, we'll end up with two numbers on the right, because when we square root a number, even an awkward number like 29/4, there are two different possible square roots. If I told you that I square something and got an answer of 25, you don't know for sure what it was that I squared. Maybe I squared 5, maybe I squared -5. So we have the principal square root, And then we have the other square root. The principal square root of 9 is the one your calculator will give you when you ask it what is the square root of 9. The other square root is the one that you automatically know about if you remember, oh, the negative of that. So we'll have 3 from the calculator, and also negative 3. In this case, that's root 29 over 4, but also negative root 29 over 4. The other thing I've done here, which you might be a little confused by, is square rooting that fraction. I ended up square rooting the top and the bottom. The square root of 29 can't be written any more simply than root 29, but the square root of 4 can. So when you see that 29 over 4 being square rooted, you can think of it as root 29 over root 4, and root 4 becomes 2. The final step is to add 7 over 2 to both sides. And traditionally, we then write that number at the front, so the plus or minus sign goes in the middle. And we get this, which maybe looks familiar to you. It's the kind of format that you would expect to see popping out of the quadratic formula. More on that later. In fact, if you want to try a bit of a challenge before we get to the quadratic formula, maybe start with a quadratic in the most general form possible, ax squared plus bx plus c. So it's got a bunch of extra letters. Think of the a, b, and c as just constants that we're happy to have kicking around all the way through our working out. See if you can complete the square and hence solve that equation to get solutions for x in terms of a, b, and c. See what you notice. The next thing for you to try once you've got to grips with this completing the square concept is questions from exercise 2c and exercise 2d. You don't necessarily have to do them all, but it's a good idea to do enough that you feel comfortable and confident and fluent with these methods. The next thing I want to look at is the quadratic formula. You've all used it, you've worked with it, maybe you sing songs involving it. I wonder if you can accurately recall this formula without looking it up anywhere. Pause the video, scribble it down somewhere, and then check back and see if you've got the right formula. Here's what you should have. When ax squared plus bx plus c equals 0, then we know that x must be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. It's quite the mouthful. It looks like a mess, but hopefully you've used it enough that it's something that is now stuck indelibly in your brain. If not, maybe you should tattoo it on your wrist or something. For example, we could solve an equation using the formula by simply pulling out the values of a, b, and c. We look at the number in front of x squared, which in this case is implied to be a 1. We look at the number in front of x, be careful with the negative sign, that's part of the coefficient of x, and we look at the constant added on at the end. Make sure the equation matches the format that was described in this statement. Without that ax squared plus bx plus c equals 0, the formula doesn't really make sense because there's nothing telling you what a, b, and c represent. But once a quadratic equation is written in that standard format, we can pull out the coefficient of x squared, the coefficient of x, and the constant term, and we can generate our solution. So in this case, we can see a is 1, b is negative 7, c is 5. We put the values into the formula, and it's a bit of a mess, but the calculator will help you out with that. And once you simplify and sort it all out, you should have 7 plus or minus root 29 all over 2. If that looks familiar, it's because it's the same quadratic I asked you to solve on the previous slide. The only difference is this time, instead of completing the square, we just substituted values into the formula. Honestly, it's not necessarily that much quicker, especially when you get fluent with completing the square. You'll find it's a really helpful technique to apply, and in many cases, it is quicker than using the formula, especially if you're doing something without a calculator. For instance, you're working on the Oxford MAT entrance exam. There are often situations where you want to deal with a quadratic and you'll find it much easier and quicker to complete the square. It also tells you more about the equation. The quadratic formula simply gives you a way of pulling out the roots of the equation. Another thing to point out here is that unless the question asks you for it, you should always leave your answers in exact form, which generally means if there are surds involved, then you need to still have surds in your final answer. In case you're curious, if you had a go at the challenge, where does the quadratic formula come from? If we start with ax squared plus bx plus c equals 0, There's a few quick steps we can follow. We could divide everything by a, and that means we just have a single x squared in front. That's useful because it will then match up with the examples we tried when we did completing the square before. And by the way, you can do this anytime you've got a number in front of x squared that isn't 1. If you're trying to complete the square with 2x squared and something, just divide everything by 2. The only thing I would caution you about there is that if you're not solving an equation, if you're just trying to rewrite an expression, you shouldn't just divide by 2, because then you'd have something half the size that you need. You should pull out 2 as a common factor of the entire expression. So keep it there with brackets around the rest of it. But you'll get to practice some of those later. The next thing I do here is complete the square. B over A is the coefficient of x, so I halve it, which gives me B over 2A, half of B over A. I've doubled the denominator, and that tells me the number that goes inside the bracket. The next thing I do is square it and subtract the square of that term. B over 2A, if we square the entire fraction, will give me B squared over 2 squared times A squared. And then the other thing I'm doing is just adding on C over A. So although it may not look like it, C over A has not been changed. It's simply been rewritten slightly. And the reason I've rewritten it in that way, multiplying the top and the bottom of the fraction by 4A, is to make life easier when I want to combine those final two terms, to simplify. And that's what's happened here. I combine those terms, I get negative b squared plus 4ac all over 4a squared. Then I take it across to the other side of the equation, so I can add b squared over 4a squared if you like, and you can subtract 4ac over 4a squared. And then you can square root both sides. Now 4a squared square roots quite nicely. 4 square roots to give 2, a squared to give a. But the top of the fraction is potentially going to be some awkward surd. So we leave it as the square root of b squared minus 4ac. Remember, we have a plus and a minus sign because there are two different potentially valid square roots. And then all we need to do is subtract b over 2a from each side. And if you look carefully, you'll find that that expression matches the quadratic formula. The only difference is, generally speaking, we put the quadratic formula over a single common denominator. So we bring that minus b and the plus minus b squared minus 4ac all together into a single numerator. So, interesting to know where it comes from. The next question I'd like you to consider, even if you didn't go through the process of completing the square, is to look carefully at the quadratic formula and ask yourself when it would break. This is a really useful technique to get into the habit of using, because there's lots of times when you have a rule or a mathematical model that is only valid up to a certain point, or there are certain conditions that will make it all fall apart. They're sometimes called edge cases, and we're looking for the particular conditions that we need to watch out for. So a good example would be, what happens if a equals 0? What would happen if we had a quadratic where a was equal to 0? And why is it that we've never had a problem with that in the past? The other thing to think about, which will help as we get on to the next topic of the discriminant of a quadratic, is what's special about that b squared minus 4ac? What kind of numbers might that be which would cause a problem for evaluating, in other words, finding the value of the right-hand side of this quadratic formula? Now you can have a go at some questions from exercise 2b, going back a bit in the book to before the completing the square section, because I think it makes a little more sense to use the formula after we know where it comes from. The next thing I'm going to look at, and this is the final part from this video, there's been a lot in it, but I'd like to finish with some visualization. Sketching a quadratic curve is a really valuable skill, and the skills and techniques you develop as you learn this will help you as you learn to sketch all sorts of other functions. So the first question is, do you know what kind of shape we're expecting? If I asked you to sketch a quadratic, but I didn't specify where it was going to go or exactly which quadratic it was, do you still have some idea of the general shape? Have a go at sketching one, maybe draw one out and see if it looks anything like the ones I'm about to show you. So here's a few. We've got a red one, a blue one, a green one. They're all quadratics. They are relatively nice looking quadratic equations, and they all cross, or at the very least touch, the x-axis at least once somewhere along the way. But there's a couple of differences. You might ask yourself which one's the odd one out and why. and you might well be able to find 3 different valid answers to that question. But let's start perhaps by matching up the equations with the graphs. You've got 3 different equations. Can you see which one goes with which graph? And can you justify your choice? Can you see why you've chosen the ones you have? Pause the video, see if you can match them up, and then come back and check your answers. All right, here's what we should have got. The red graph is y equals x minus 2 in a bracket squared. Bringing back what we were talking about with completing the square, this is a perfect square, x minus 2 times x minus 2. That is the reason that there is only a single value for x that makes the quadratic curve equal to 0. It doesn't dip below the x-axis and then come up later. It dips to the x-axis and then bounces right back up. Sometimes known as a repeated root or just a single solution. If you're trying to solve x minus 2 in a bracket squared equals 0, in other words, you want to replace y with 0, then you're asking the question, where does my curve cross the x-axis? And the answer would be, well, either when x minus 2 is 0 or when x minus 2 is 0. There are 2 brackets, but they're the same. So your 2 solutions are the same. They're both x equals 2. For the next one, you can also solve. If you replace y with 0, we get either 2x equals 0 or x minus 6 equals 0. Well, if x minus 6 is 0, that means x has to be 6. And if 2x is 0, that means x has to be 0. So we're looking at the green graph. It crosses at 0 and at 6 on the x-axis. And finally, the blue graph. This one is a negative quadratic. There's a minus sign in front of the x squared term. And that means that instead of coming down from very high up and then having a minimum point and going back up, it starts low, has a maximum point, and then goes down again. So we've got a sort of this is as good as it gets moment in the blue quadratic. So in general, and this advice at the beginning is valid for any curve you're sketching, if you set x equal to 0 and solve for y, that will tell you the y-intercept, the point where the graph crosses the y-axis. And that's because the y-axis is effectively the line x equals 0. It's the line that is 0 distance to the right or left. Similarly, y equals 0 is the horizontal line that lies on the x-axis. So if we set y equal to 0, it's equivalent to saying, when does the line that sits on the x-axis cross my quadratic? Now, the first of those, setting x equal to 0, is the simplest, because if you make x equal to 0, the x term disappears, the x squared term disappears if it's written in that format, and everything cancels down and you just read off a single value for y. Quadratics will only ever cross the y-axis in one place. But setting y equal to 0 means you have to solve a quadratic equation, and that's why you potentially have 2 different solutions, and possibly just 1 repeated solution, and even maybe no solutions at all. It's also worth pointing out here, if you've got a quadratic where the coefficient of x squared is positive, then it has a minimum somewhere. It's a smiley face quadratic. And if the coefficient of x squared is negative, it has a maximum somewhere. A good way to think about this that will generalize nicely to more complicated functions is to treat the x squared term as the dominant term. Imagine x was a very large number, like 1,000 or 1,000,000. Well, however big a, b, and c are, if x is allowed to get big enough, then doing b times x is going to be much, much bigger than c. But doing a times x squared will give you a much, much bigger answer than b times x. If x is 1,000, for instance, then maybe we're dealing with 3x squared plus 4x plus 5. We're doing 3 times 1,000 squared plus 4 times 1,000 plus 5. Well, the 5 is massively insignificant. Even the 4,000 is insignificant compared to the 3,000,000. And the bigger x gets, the more significant the x squared term becomes and the less significant the others become. We talk about the long-term behavior of a function or a graph. In other words, as x gets very, very big, what happens to y? Or as x gets very, very low, massive negative numbers, what happens to y? And for a quadratic, that is dictated exclusively by the number in front of x squared. So if you've got a negative quadratic, in the long run, you're going to have negative values coming out the other side. And if you've got a positive quadratic, you'll have positive values for very large x values or very low x values. Remember, even if x is negative, if it's a big negative, when you square it, you get a massive and positive number. It's worth pointing out here, if you're interested in exactly where the maximum or the minimum point might be, you can find that information out by completing the square. I'm not going to go into that process right now in this video, but you can look it up or you might remember it. Alternatively, by putting the values into the ClassWiz calculator, it will tell you not just the roots of your quadratic, the 2 points where it crosses the x-axis, but also the coordinates of the maximum or the minimum of that quadratic. Give you the x-coordinate of the minimum or maximum and the y-coordinate. So that's very helpful. You might want to try that out for this one. Have a go at sketching it without a calculator first, and then plug the numbers 1, 4, and -5 into the calculator function and see if it agrees with you about the crossing points and the vertex. Here's how I would do this one. I'd start by finding the y-intercept by setting x equal to 0. So instead of x squared, add 4x minus 5. I have nothing squared, add 4 nothings, take away 5, which is minus 5. Much like the y equals mx plus c straight line graph, all we need to look at when a quadratic is written in its standard form is the number at the end. That'll give us the y-intercept. So the curve definitely crosses the y-axis at 0, -5. To find the x-intercept, or x-intercepts, depending on how many there are, we would have to solve the equation with a y equals 0. Well, that means we have a quadratic equation, so we need to solve our quadratic. I've not shown you the method I've used here. You could factorize, you could complete the square, you could use the formula. In fact, I'd encourage you to stop and have a go at all 3 of those methods and ask yourself which one felt like it was the most efficient, which one took the most thought, and which one felt like the kind of thing you could do automatically when you're on autopilot in the middle of a busy question. Which one are you most likely to get right? And also, once you've got your answers, I wonder how many of you substituted the numbers back in to double check that they worked. It's not a very long process. 1 squared, add 4 ones, take away 5. Yes, that's 0 because it's 1 add 4 minus 5. -5 squared is 25. When we add 4 lots of -5, we're taking away 20. And then we take away another 5 and we're down to 0. So it convinces us we've done it right. Even if you solve this on a calculator, it's a good idea to do a quick check because we put incorrect numbers in calculators just as often as we miss out minus signs when we're writing down our working out. It's very tempting to trust the calculator to give you the right answer all the time. All the calculator will do is give you the appropriate answer for the question you asked it. So if you ask it the wrong question, it'll give you the wrong answer. Well, now we have the x-intercepts, 1, 0 and -5, 0. The last thing you might do is find the minimum. And I'm briefly going to talk about this because it's on the screen. You might spot a pattern, a link between the completed square form of this quadratic and the coordinates of the vertex, the minimum point. Well, if you have something squared, no matter what the number inside might be, because we don't know x could be anything, you pick a number that could be anything and you add 2 to it, could still be anything, but then you square it, and you now know for sure that the answer to that is never negative. It could be 0, it could be positive, but it can never be negative because you got it by squaring something. You square something positive, you get a positive answer. Square something negative, you get a positive answer. Square 0, you get 0. So we know for sure that that stuff circled in red is no lower than 0. And that gives us a hard lower limit to work with. When you take away 9 from something which is definitely no lower than 0, you may go as low as -9, but you can't go any lower. It's a bit like having one bank account that doesn't let you go into debt, has no overdraft facility at all, and then another bank account that you've just opened that does let you go into debt. Now let's imagine we don't even know what's in the first bank account. All we know is that it was a child's bank account that doesn't let you go into debt. Now you've just spent £9 that you didn't have in the other account. The worst case scenario is that you were stony broke originally, you had no money in the other account, and now you're in debt £9. But it's not possible for you to be in debt anymore because the worst case scenario for the bank account with no overdraft facility is that you have no money. You can't do any worse than nothing if you're not allowed to go into debt. So that tells us that the minimum value must be -9. That is the lowest number that can come out of that quadratic expression. The other part of this is, when does that happen? Well, the lowest number we know happens when the squared bit is 0. How do we make the squared bit 0? Well, we need x add 2 to be 0, so that when we square it, we get 0. And the way we make x add 2 equal to 0 is by setting x to be negative 2. So a little bit like factorizing that last bit, we're saying what makes the bracket 0? Whatever makes the bracket 0, that's the x-coordinate of the minimum point. And whatever we get as the value of y when the bracket is 0, that's the y-coordinate of the minimum point. And our graph should look something like this. I've marked on the two x-intercepts. You can see those at 1, 0 and minus 5, 0. We can also see the y-intercept there at negative 5. And I've also included the vertex minus 2, minus 9. Incidentally, if you're asked for the line of symmetry, all quadratics that you're going to come across here that are written in the form y equals something x squared plus something x plus something, they all have a vertical line of symmetry. And it's just the vertical line that goes through the vertex. So in this case, the equation of the line of symmetry is x equals negative 2. It's all the points with an x-coordinate of negative 2. If you want a bit of an extra challenge, have a think about how you might go about sketching or making a reasonably accurate sketch of a curve with no roots, a curve that doesn't cross the x-axis at all. You could try this one if you like, x squared add 4x add 5 instead of the one that we just did, x squared add 4x minus 5. See if you can find a way to accurately sketch that, and then maybe compare it to the sketch of the example, see what you notice. The last thing you can have a go at is questions from exercise 2F. These test you on drawing graphs from various different quadratics, so it will help you to practice all of the other skills. Sometimes you'll use the formula or you'll use the calculator to get some quick, easy answers. You might complete the square so that you can see where the minimum or maximum point might be. And you will start to build a familiarity with these functions that you will rely on throughout the whole of your course.